Dear students, in our linear algebra part, we will discuss one very important and interesting topics of linear algebra which helps us to decide the existence of the solution or not. That is the rank of a matrix. Very important terms, very important concepts, but very easy to understand. Okay, so let us see what is the rank of a matrix. Rank of a matrix. So I am writing the definition. So there are two definitions. So our matter of discussion is rank of a matrix. What is the rank of a matrix? It is the maximum number of linearly independent rows. Okay. In our previous video, we have discussed what is linear independent vectors or linearly dependent vectors. For your reference, I will give the link in the descriptions. If you have missed that video, you can go through it. So matrix A is 1, 2, 3, 2, 4, 6 and 1, 1, 2. This is the matrix and we have to find the rank of this matrix. Okay. So we will go for the row operation. So question is find rank of A, and it is denoted as, the rank of A is denoted as row of A. This is the notation. Okay, this is the notation of the rank of a matrix. So we have to find the rank of this matrix. So solution. So you see how we do it. You see, in the previous class we have discussed Gaussian. That is most important for this linear algebra. So here the given matrix is 1, 2, 3, 2, 4, 6, 1, 1, 2. Then from this matrix we go to the row reduced form. That is, first row is intact, that is 1, 2, 3. Second row we make these two elements 0, that is with 0, 0. How we make this 0? That is row 2 minus 2 row 1, and this is row 3 minus row 1. That property we will apply to the entire row. So this minus 2 into this 0, this minus 2 into this, that also 0, this 6 minus 2 into 3, that also 0, then this minus this, 1 minus 1, 0, 1 minus 2, that is minus 1, 2 minus 3, that is minus 1. Okay, so we can rewrite it as 1, 2, 3, 0, minus 1, minus 1, 0, 0, 0. Okay, just we rewrite row 2 and row 3, just we exchange. Now you see how many non-zero rows are there? There are two non-zero rows are there. Okay, so these two non-zero rows we call as a linearly independent vectors when we have discussed in the previous classes. So here the definition is maximum number of linearly independent rows. So these two rows are linearly independent because by any means we cannot make 0 by row operations of these two. That is why these two rows are linearly independent rows. So if this matrix is A, then the rank of A is equal to 2. Now we have discussed that how we find the linearly independent rows, and by that we decide the rank of a matrix. Now you come to the second definitions. We will work out the same problem, but we will use this second concepts, that is non-zero minor form. Okay, what is non-zero minor form? Let us work out the same problem. So matrix A is, how we work out this? It is the order of the largest non-zero minor matrix. So this is a matrix of order 3 cross 3, right? First you find the largest square matrix from this. So that is itself. Then find its determinant value. So what is det A? Det A. Det A, the value is 1 into 4 into 2, that is 8 minus 6. Then minus 2 into 2 into 2, 4 minus 6. Then plus 3 into 2 into 1, 2 minus 4. That is 8 minus 6, that is 2. 4 minus is minus 2 minus, that is plus 4. Then 2 minus 4, that is minus 2 into 3, that is minus 6. So that equal to 0. Okay, as we get determinant A is equal to 0, then the rank of this matrix is not 3. Rank of A is not equal to order of A, that is 3. That means here the rank of the matrix is not 3 because we are getting the determinant value 0. But if suppose this is the matrix and we find the determinant value and we get the determinant value is not 0. Okay, if this determinant value will not be 0, then its rank will be 3. That is order of matrix. So what is the note down? If order of the matrix is equal to, if the determinant of the value of the matrix is not 0, then order of that square matrix is the rank. But here that fails because here order is 3 but its determinant value is 0. So let us come for the next lower order. So this is a 3 cross 3 matrix. So as determinant value is 0, so consider lower order matrix. That means you can consider 1, 2, 2, 4. You can consider 2, 3, 4, 6. You can consider 2, 4, 1, 1. You can consider 4, 6, 1, 2. You can consider 1, 2, 1, 1 like that. So you can construct so many square matrix of order 2 because this was 3 cross 3. Then we construct the next lower order square matrix and find the determinant value of 1 by 1. So what is the value of this? This is 4 minus 4. This is 4 minus 4, that is 0. Its value is 0. Its value is 0. Its value is 2, 4, 1, 1. Its value is not equal to 0. So determinant value is not equal to 0. So we are getting so many 2 cross 2 determinant matrix and we find the determinant value of each matrix if among all the square matrix we get at least one matrix whose determinant value is non-zero, then look what is the order of that matrix. Order of that matrix is 2. This matrix is called as the minor matrix and that minor matrix is a non-zero minor matrix. And what is its order? What is its order? Its order is 2. So order of minor matrix is equal to 2. Order of non-zero minor matrix, order of, so this implies order of non-zero minor matrix is equal to 2, implies rank of A is equal to 2. So these are the two techniques by which we determine the rank of the matrix. Okay, one is the row operation method, other is the determinant method. Dear students, already we have discussed how to find the rank of a matrix in two different methods. The first one is by row reduction process, and that says the number of non-zero rows that equal to the number of linearly independent vectors indicates the rank of a matrix, and the second method is the minor matrix method. Okay, now let us discuss some important properties of the rank. The first property is, if we are given a matrix A, then rank of A is equal to rank of A transpose. You know what is the transpose of matrix? You see, this is the given matrix A. We have considered 1, 2, 3, 2, 1, 1, 2, 3, 1. Then by row operation, this matrix reduces to this 1, 2, 3, 0, minus 3, minus 5, 0, minus 1, minus 5. How we have changed this? That is, row 2 is changed by row 2 minus 2 row 1. Row 3 is changed by row 3 minus 2 R1. So by applying this property, we have changed this matrix to these conditions. And these operations are applied on this matrix to give this. Similarly, again we apply this row operation R3 is equal to 3 R3 minus R2 on this matrix to give this one. And this is the row reduced form. This is in echelon form. Now you see how many non-zero rows are there? There are 3 non-zero rows are there, and that 3 rows are linearly independent. So for this matrix A, the rank is 3. Rank of A is 3. Then you come to the transpose. If A is 1 2 3 2 1 1 2 3 1, then A transpose is, this row is written as a column 1 2 3, then second row 2 1 1 in the second column, that is 2 1 1, third row is 2 3 1, that is written in third column, that is 2 3 1. Then we apply this row operation. Row 2 is equal to row 2 minus 2 R1. We will apply this law in this matrix, and row 3 is equal to row 3 minus 3 R1. Also we will apply this property on this matrix. That gives this new matrix 1 2 2, 0 minus 3 minus 1, and 0 minus 5 minus 5. Okay, just for your reference I am explaining. R2 means this row is changing by R2 minus 2 R1. You see, this is R2, this is R1. You multiply 2 to this, then this minus this, 2 into 1 2, this 2 minus 2 is 0. Then 2 into 2 4, this 1 minus 4 minus 3, 2 into 2 4, then 3 minus 4 minus 1. So like this we have applied these two row operations on this matrix to get this one. Similarly, apply this property on this matrix. Row 3 is formed by 3R3 minus 5R2, that gives this matrix. Okay, how many non-zero rows are there? There are 3 non-zero rows are there, and that 3 are linearly independent. So we say rank of A transpose is also 3, that is rank of A equal to 3 is equal to rank of A transpose. So this is one important property of the rank of a matrix. Now you see the second property. The second property says if A is a matrix and data is not equal to 0, means the matrix is non-singular. When the matrix is non-singular, for the given matrix A, we can find its A inverse, and rank of the matrix A is equal to rank of the A inverse. So this is the matrix A, 1 2 3 2 1 1 2 3 1. Then we apply this row operations, row 2 and row 3 on this, we get this one, 1 2 3, 0 minus 3 minus 5, 0 minus 1 minus 5. Okay, how you see? You see how we operate these operations. R2 means this is changed. How? R2 minus 2 R1. So this minus 2 into this 0, this minus 2 into this. So 1 minus 4, that is minus 3. This C to 2 into this, 1 in minus 6, that is minus 5. Similarly, we have applied this row on this to get this one. Okay, once we get this, then apply row 2 or use row 2 to make this element as 0 by this property. R3 is forming by 3R3 minus R2. So apply this property on this, using this, you will get this. That is 3 into this, that is minus 3, minus of this, plus, that becomes 0. 3 into this, that is minus 15, minus of minus plus, that becomes 10. So now we get 3 non-zero rows, implies the rank of A equal to 3. And you know how to find the inverse of a matrix. The inverse of a matrix, A inverse is equal to adjoint A by determinant A. This is the formula to find the A inverse, what already you have learned in the lower class, that is class 12. Now we will discuss the second property of the rank. The second property says if A is a matrix and which is non-singular. Non-singular means A will have inverse. Then the rank of A is equal to rank of A inverse. This is the second property. You see, we have considered a matrix A and the determinant value of this matrix is not 0, means its inverse exists. Then we go for the row operations. Using row 1 to make this element and this element of row 2, row 3 as 0. So we define these properties. R2 is R2 minus 2R1 and apply this law to this row. R3 is R3 minus 2R1, apply this law to the third row. By applying that law, we get this matrix. Okay. Then from the second matrix come to this. So this is the law, R3 is 3R3 minus R2. You apply this law to the third row, we get this matrix. And there are 3 non-zero rows, so we claim rank of A is 3. Then you come to the inverse. In your class 12, you know if A is a non-singular matrix, then rank of A is equal to adjoint A by determinant A. By applying that formula, we have found out the inverse of this matrix. 1 by 10 and this. So this is the inverse of this matrix. So let us find the rank of this matrix. So 1 by 10 is constant. So we can write it as like this. Okay. So 1 by 10, then we reduce this matrix by row operations. Already this element is 0, so no need to change second row. We have to change this. So row 3 is row 3 minus plus 2R1. Okay, so this becomes 0. So that property will apply for the rest of the two elements. So we get this. Then applying row 2, we make this one as 0. So that is row 3 is row 3 plus 3 R2. So we get this. So here also we get 3 non-zero rows. So rank of A inverse, that is also 3. Hence rank of A is equal to rank of A dash or A inverse. This is the second property. Now we will discuss the third property, that is, if A is a matrix of order m cross n, then the rank of A is less than equal to minimum of mn. Okay, that means m and n are rows and columns. Now I am giving you two examples. Here A is this matrix. This matrix is a matrix of order 3 cross 4. I am giving you this example. A is equal to 3 cross 4 matrix. Then by applying this property to row 2 and row 3, we get this one. Then we apply this property to this matrix. On this row 2, we get this matrix. Now you see, we are getting a 3 cross 4 matrix where 3 rows are non-zeros. As 3 rows are non-zero and that are linearly independent, we can say a row of A is 3 and that 3 is nothing but the minimum between 3 and 4. Okay, so our loss is either the row rank of A will be less than this or equal to this. So this example shows rank of A is equal to minimum of mn. Then you come to another example. So this is B. Okay, so by row operations, row 2 is row 2 minus 2 R1 and R3 is R3 minus 3 R1. We apply these two property on row 1 to change row 2 and row 3, and this is the matrix. We apply this property in second, we apply this property in third, so this gives the matrix. Then row 3 is row 3 minus row 2, so that makes the last row as 0. We get 2 non-zeros. Okay, so rank of B is 2. So rank of A is less than equal to minimum of mn. Here we have proved minimum of 3 4 is 3, so this is minimum. Here 3 4, order is 3 4, so minimum of 3 4 or less. Or less means here it is 2, means rank of A is either equal to minimum of mn or less than minimum of mn. So this satisfies the property. Now we will discuss the property 4, which is related to the value of a determinant. You see, A equal to Aij n cross n. So this is a square matrix of order n. Okay. Then law says rank of A is equal to n when determinant A is not equal to 0, or if determinant A is not equal to 0, then the rank of A equal to n. You see this example. A is this and its determinant value is not 0. As determinant value is not 0, its rank will be 3. If you go for row operation, you just take it as a homework. If you go for row operation for this matrix and you will convert it to the row echelon form, then you will find there are 3 non-zero rows. That is why the det A not equal to 0 implies rank of A equal to 3. Then second property. When det A equal to 0, then the rank of A less than A. You see, B is this 1 2 3 2 1 1 2 4 6. That implies det B equal to 0. As det B equal to 0, its order is 3 cross 3 means 3. As det B equal to 0, so rank of B will be less than 3. So we conclude that det A is not equal to 0, rank of A equal to order of this 3 is rank of A equal to 3, that is order of A, and det B equal to 0 implies rank of B less than 3, so that is rank of B less than order of B. This is another property, that relation of rank to solution of non-homogeneous equations. This is very important. In Gauss elimination process, we have solved the solution of non-homogeneous equations and solution of homogeneous equations. Now we will interrelate that fact to the rank. Okay, I am considering one case. Suppose in case 1, this is our matrix after the row reduction form. Okay, after row reduction, you see in the coefficient matrix part where I have written A, B, C, D, the letters, so that is the numbers, and somewhere I have written the zeros. You see, these are the zeros. Okay, so now you look at the system. So here A is a matrix Aij of order 4 cross 4. This is the coefficient matrix, and here the matrix AB, that is the augmented matrix, is a matrix of order 4 cross 5. What is the rank of A? Rank of A is 4. Why? After row reduction, you see this is a non-zero row because A, B, C, D are there. This is a non-zero row, F, G, H are there. This is a non-zero row, J, K are there. This is a non-zero row, that is M are there. That means there are 4 non-zero rows. So rank of the coefficient matrix is A. When we come to the augmented matrix AB, there also the rank is 4 because in AB also the number of non-zero rows are 4. So we conclude if rank of A equal to rank of B is equal to number of unknowns. How many unknowns are there? There are 4 columns in the coefficient matrix. So 4. If that situation occurs, means coefficient matrix rank, augmented matrix rank, and the number of unknowns, then that will give us the idea that unique solution will exist. That is case 1. Then we come to case 2. This is the case where this part is the coefficient matrix A, B, C. This is a 3 cross 3 matrix I have considered. So in this 3 cross 3 matrix, we have considered A as a 4 cross 3 matrix. A is, there are 4 rows, 1, 2, 3, 4. In coefficient matrix I have considered 4 cross 3 matrix, and in the augmented matrix there are 4 rows and 4 columns. Okay, 4 rows and 4 columns. Now you see rank of A is 3. Rank of A is 3 because there are 3 non-zero rows. But if you look at the augmented matrix, rank of AB, that is 4. Rank of A is 3 because there are 3 linearly independent rows. Rank of AB is 4 because there are 4 number of non-zero rows. This is non-zero row, this is non-zero row, this is non-zero row, this is non-zero. So rank of A and rank of B are not same. If that situation happens, then we conclude that there is no solutions. Okay, one case rank of A and rank of B same. Another case rank of A and rank of B are not same. Okay, now we will come to the another case. So here rank of A is equal to 3 because there are 3 non-zero rows. Rank of AB is also 3 and N is 4. Okay, so as rank of A and rank of B are same, so we should have unique solution. But the problem is rank is 3 but number of unknowns or variables are 4. So as rank of A is equal to rank of A condition A, rank of A, and that means rank of coefficient matrix, rank of augmented matrix are same but and less than number of unknowns. In case 3, we have considered a system of equations where 4 unknowns are there because there are 4 columns, means 4 unknowns are there, and there are 4 equations also. But after row reductions, we find the final matrix as this. That means in the coefficient matrix there are 3 non-zero rows. In the augmented matrix also there are 3 non-zero rows. So rank of coefficient matrix A is 3. Rank of augmented matrix row of AB is also 3. So as these two are same, so we should have the unique solutions, but the question will not be like that. We will count the number of unknowns. The number of unknowns is 4. As rank of A is equal to rank of AB less than number of unknowns implies infinite solutions. So these are the different cases which are given the conclusion regarding the existence of solutions by using rank in case of non-homogeneous system of equations. Now we will discuss the relation of a rank to the solution of homogeneous system of equations. And you know, the homogeneous system of equations means we will have a system of equations, but in every equations the right hand side after the equal sign will be 0. Okay, so in that case also rank helps us whether the solution of system of equations will exist or not. If exist, whether it is trivial or non-trivial. So now we come to the different cases. Now we will discuss the relation of a rank to the solution of homogeneous system of equations. You know that homogeneous system of equations, the right hand sides are all 0 in every equations. See, that is why in this augmented matrix, you see the last column I have mentioned 0. Okay, that is why in homogeneous system of equations no need to calculate the rank of the augmented matrix, because the rank of the augmented matrix and rank of the coefficient matrix will not have any relation, because rank of the coefficient matrix will be same as the rank of augmented matrix, as augmented matrix last column is 0. Right. Now we come to the case 1. In case 1, you see this is the structure after the row reductions. Right. Here how many unknowns are there? There are 4 unknowns, because 4 columns are there, so number of unknowns are 4. What is rank of A? Means how many number of linearly independent rows are there? This is one non-zero row, this is second non-zero row, this is third non-zero row, this is fourth non-zero rows. So as there are 4 non-zero rows and they are linearly independent, we can say rank of A is 4. Okay, so rank of A is 4 and number of unknowns are 4. So rank of A is equal to number of unknowns. When that situations happens, rank of the coefficient matrix and number of unknowns are same, then that case is the trivial solutions. Means that system of equations will not have any other solutions other than 0. All the variables of x1, x2, x3, x4 are 0 here. Okay. Then you come to the second case. In second case, number of unknowns are 4, because A, B, C, D, there are 4 columns, means in the system of equations there will be 4 unknowns. But after row reductions, what we get? We are getting 3 non-zero rows. Row 1 is non-zero, row 2 is non-zero, row 3 is non-zero. Okay, so that is why rank of A is 3. So what is the relationship? Here rank of A is less than number of unknowns. When this situation happens, rank of the coefficient matrix is less than the number of unknowns, we say the solution exists. Solution exists, but the solution is non-trivial case. Means for this system of equations we will have infinite solutions. We will have infinite solutions.